Let us begin slowly and set the mood of the subject in a calm and careful way. Tonight we are thinking about large language models, and more specifically about reasoning, prompting, and hallucinations in large language models. These topics sit near the center of modern machine learning, and also near at the center of many misunderstandings. So we will move carefully. We will not rush. We will return to the same ideas from different angles. And as we do that, the structure of the subject may begin to feel less mysterious. At a very high level, a large language model is a system trained to continue sequence. It sees words broken into pieces, and from a long history of earlier pieces, it predicts what piece is likely to come next. That description sounds simple. In a way, it is simple. But from that simple setup, a very rich collection of behaviors appears. Some of those behaviors look like memory. Some look like style. Some look like planning. Some even look like reasoning. And some, importantly, look like confidence without truth. So the key question is not only what the model predicts, but how those predictions are turned into actual generated text. The key question is also how the prompt shapes the model's behavior, how confidence should be interpreted, why hallucinations arise, how external information can help, and whether something like reasoning can emerge from a machine trained only to predict the next piece of language. Let us pause and reflect. There is already a deep idea here. A model may define a distribution over what could come next, but generation requires a choice. A probability distribution is not yet a sentence. It is not yet an answer. It is not yet a paragraph. It is a structured uncertainty over possible continuations. To go from uncertainty to an actual output, one needs a decoding rule. And this is where much observed behavior begins. So let us begin with sampling, decoding, and randomness in generation. When a language model has processed a prompt, it does not simply contain one inevitable next word. Instead, it has a ranked landscape of many possible next words or word fragments. Some options receive more weight, some receive less, but usually many are possible. Training has shaped that landscape. Training says, in effect, given a context like this, these continuations fit the patterns of the data better than those others. But training does not itself force one continuation to be selected when a model is used. That selection is the job of decoding. One decoding rule is very simple. One may always pick the most likely next token. Then, after that choice is appended, one repeats the process. At every step, the model looks at the full sequence so far and again chooses the single most likely next token. This is often called greedy decoding. The name is suggestive. It means that at each local moment, the system grabs the highest immediate probability option. Greedy decoding has a certain appeal. It is stable. It is deterministic. If one gives the same prompt, one gets the same answer. It also often gives fluent text. And yet it can be limited. Why? Because the locally best choice may not lead to the globally best sequence. A sequence of individually safe decisions may become repetitive, bland, or stuck in patterns. The model may overcommit to one path too early. So people often use sampling instead. Sampling means that rather than always choosing the most likely token, one draws from the model's predicted distribution. More likely tokens are still favored, but less likely ones may sometimes be selected. This introduces randomness. And that randomness can produce variety, creativity, and more natural-sounding alternatives. It is worth repeating that the randomness is not replacing the model. The model still provides the probabilities. The randomness acts after that, during decoding. The model says what seems plausible. The decoding strategy says how boldly or cautiously we walk through that space of plausibility. This distinction matters because users often speak as if the model itself changed dramatically when, in fact, the decoding will change. A model can appear more rigid or more imaginative depending on how its outputs are sampled. The observed behavior is therefore a joint product of the trained system and the decoding method. There is a deep trade-off here between diversity and reliability. When one samples more freely, one can obtain outputs that are less repetitive and sometimes more insightful. But at the same time, one increases the chance of drifting into low probability regions where mistakes, inconsistencies, or fabrications become more likely. When one decodes more conservatively, one may obtain safer and more stable outputs, but also more generic ones, sometimes with a narrow and overconfident flavor. So decoding is not a minor technical detail. It is part of the behavioral interface of the model. It changes what we see. It changes how the model feels to interact with. It changes the degree of surprise, the degree of variety, and often the degree of factual reliability. Let us pause and reflect again. A language model after training is like a very complicated map of conditional possibilities. Decoding is the policy that turns that map into a path. If the path always follows the steepest local slope, it may become predictable and narrow. If the path includes controlled randomness, it may explore more, but it may also wander. So when we ask why a model behaved in a certain way, we must ask not only what it learned, but how we sampled from what it learned. Now let us move naturally into temperature, top K, and nucleus sampling. Temperature is one of the most famous controls in language model generation. The word itself is metaphorical. It suggests heating or cooling a distribution. When the temperature is reduced, the predictive distribution becomes sharper. The model's most favored options become even more dominant relative to the rest. When the temperature is increased, the distribution becomes flatter. Less favored options become more competitive. So low temperature means more concentration, more determinism, more caution. High temperature means more spread, more randomness, more willingness to explore unusual possibilities. In practice, this can strongly affect style. A low temperature answer may feel crisp but rigid. A high temperature answer may feel vivid but unstable. Again, it is worth repeating that temperature does not retrain the model. It does not inject new knowledge. It reshapes how the already learned predictive weights are used at generation time. So temperature is best understood as a decoding control, not a model change. This is conceptually important because it teaches us a general lesson: output quality depends both on the model and the decoding strategy. A powerful model with poor decoding settings can behave poorly. A weaker model with careful decoding can appear surprisingly solid in narrow contexts. Of course, the model still matters enormously, but the route from learned distribution to metatext has structure of its own. Now consider top K sampling. Here the idea is to look only at the top few candidate tokens at each step. Instead of allowing every possible next token to remain in play, one truncates the set and keeps only the top group by probability. Then one samples from that reduced set. This gives controlled randomness. The model is still allowed to vary, but not by reaching too far into the low probability tail. Nucleus sampling works similarly in spirit, but differently in construction. Instead of fixing a number of candidates, it keeps the smallest set whose total probability exceeds a certain threshold. So the number of retained options can vary from step to step. If the distribution is sharply peaked, the nucleus may be small. If the distribution is broad, the nucleus may be larger. This is a subtle and elegant idea. It means that the truncation adapts to the uncertainty of the model at that moment. Where the model is confident, generation becomes more concentrated. Where the model is uncertain, more options remain available. Both top K and nucleus sampling are probabilistic filters. They are not new models. They do not create intelligence that was absent. They shape the region of the output distribution from which the next token may be drawn. So again, we see the same principle. Behavior arises from the combination of learned probabilities and decoding rules. Let us say that another way. The model provides a landscape of possible next steps. Temperature changes the relative steepness of that landscape. Top K cuts away everything except the most likely peaks. Nucleus sampling keeps only enough of the landscape to capture most of the probability mass. Then sampling chooses within that filtered space. Why do these methods matter so much? Because generation is sequential. A small choice early in the sequence changes the context for later choices. Later probabilities are conditioned on earlier generated text. So decoding decisions accumulate. They do not merely affect one token. They redirect the entire unfolding of the response. This is why two outputs from the same model and the same prompt can diverge so significantly under different sampling conditions. Small local perturbations can lead to large global differences. The process is path-dependent. Once a phrase is chosen, many later probabilities shift. Once a topic is framed a certain way, later continuations become more likely in that frame. It is worth repeating that observed model behavior is not only a property of training. It is also a property of sequential generation under a chosen decoding rule. This is one of the reasons why language models can feel both stable and unstable, both consistent and variable, depending on how they are used. Now let us move into one of the most fascinating features of large language models in context learning as conditional adaptation. In context, learning refers to the phenomenon that a model can change its behavior in response to the prompt, sometimes dramatically, without any update to its parameters. No retraining occurs. No gradient step is taken. The weights remain the same. And yet, when shown instructions, examples, patterns, or role framing, the model often adapts. This is surprising because in more traditional machine learning, learning usually means changing parameters through training. Here, however, something that looks like learning can happen within the context window itself. The model sees the prompt, interprets it as part of the sequence, and produces outputs that reflect the structure of that prompt. So what is happening? The safest conceptual language is that the model is performing conditional adaptation. It is not changing its long-term stored parameters. Rather, it is changing its immediate behavior by conditioning on the prompt. The prompt acts as information, and conditional probabilities depend on information. This is an important mathematical viewpoint. We should not think of prompting as magic. We should think of prompting as changing the conditioning event. If the model is asked a question directly, it conditions on one context. If the model is shown 3 examples and then a 4th incomplete example, it conditions on a different context. If it is framed as a tutor, a translator, or a formal assistant, again the conditioning context differs. The same model, then, can behave differently because the conditional distribution over next tokens has changed. The prompt does not rewrite the model's weights, but it reshapes the local statistical problem the model is solving. Let us pause and reflect. This is one of the most surprising mathematical phenomena in modern machine learning. A fixed system can display context-sensitive behavior that resembles task adaptation, style adaptation, and even limited strategy adaptation simply because the prompt changes the probability landscape. Examples in the prompt matter because they alter the sequence pattern the model is continuing. If the prompt contains several input-output pairs, the model may infer that the continuation should follow the same pattern. If the prompt contains careful reasoning steps, the model may continue in a reasoning-like register. If the prompt contains terse answers, the continuation may become terse as well. We should be careful, however. The phrase in context learning can tempt us to overstate the phenomenon. The model is not necessarily learning in the deep and durable way that humans do. It is not building a permanent concept inside its parameters during the interaction. But it is adapting conditionally, and that adaptation is often powerful enough to mimic learning at the behavioral level. So prompting becomes a study in conditioning. And that brings us naturally to the mathematics of prompting. Prompting can be understood as reshaping the conditional distribution of the next token. This simple sentence contains a great deal. A prompt is not merely a request to the model. It is a sequence that becomes part of the model's statistical conditioning context. Every instruction, every demonstration, every formatting cue, every role framing, and every prior example changes the sequence the model sees. Therefore, it changes what comes next. Instruction prompting says, in effect, continue in a way consistent with these instructions. Demonstration prompting says, continue in a way consistent with these examples. Role framing says, continue in a way consistent with this persona or communicative mode. Structured formatting says, continue in a way consistent with this organization of information. All of these are variants of conditioning. They are ways of steering the local predicted distribution without changing the underlying parameters. It is worth repeating, prompting is not magic. Prompting is conditioning. That is one of the clearest conceptual anchors in this subject. Of course, the full story is richer. Prompts may activate different internal features, different latent patterns, and different algorithm-like routines inside the network. But from a probabilistic point of view, the cleanest first interpretation is still that prompts change the information set on which prediction is conditioned. This is why good prompts often help. They reduce ambiguity. They put the desired structure closer to the surface. They select a narrow region of the model's behavioral repertoire. And this is also why vague prompts can lead to vague answers. If the conditioning context is broad, many continuations remain plausible. So when people ask how prompting works, a mathematically disciplined answer is this: prompting works by altering conditional probabilities through context. The model is always predicting what comes next, but what comes next depends on what has already been said. Let us pause and reflect again. When we prompt a language model, we are not pulling a hidden lever labeled intelligent. We are changing the sequence. By changing the sequence, we change the conditioning. By changing the conditioning, we change the effective computation and the likely output. This is simple to state, but very deep in consequence. Now we turn to probabilistic calibration and confidence. A model often produces text that sounds certain. It may use polished language. It may answer smoothly. It may present claims without hesitation. But sounding certain is not the same as being well calibrated. Calibration refers to the agreement between predicted probabilities and actual frequencies. Informally, if a system says an event has a certain probability, then across many such cases, that event should occur at roughly the frequency. Good calibration means that uncertainty estimates align with reality. Poor calibration means that stated confidence and actual correctness drift apart. In language models, calibration is especially tricky because the system outputs sequences of tokens, not simple one-step classifications. It can be locally confident about word choices while globally wrong about the factual content. It can also produce fluent prose that gives a strong impression of understanding even when its uncertainty is poorly represented. This distinction between fluency and trustworthy uncertainty is essential. Fluency is about producing plausible language. Calibration is about whether confidence tracks truth. These are not the same thing. A model can be very fluent and poorly calibrated. In fact, much of the danger of hallucination comes from exactly this mismatch. It is worth repeating that polished language can conceal uncertainty. The model is trained to continue text in a way that resembles its data. Human writing often presents claims confidently. So the model can learn the style of confidence without possessing a robust mechanism for factual self-verification. The result is an output that sounds reliable even when it is not. This matters a great deal for evaluation and safety. If a system is miscalibrated, then users may trust it too much. They may mistake verbal smoothness for epistemic trustworthiness. It may fail to distinguish between high-probability language and verified fact. So calibration is not a minor statistical footnote. It is part of the practical meaning of model confidence. It asks whether the system's uncertainty, however represented, corresponds to actual correctness. Now we arrive at one of the most discussed phenomena in language models, hallucination. Hallucination refers to confident generation not grounded in truth. The model says something that is false, invented, unsupported, or distorted, often in a smooth and convincing style. This is sometimes described as a bug, but that description is too shallow. Hallucination is better understood as a statistical and structural phenomenon arising from the way the model is trained and used. Why does it happen? Because the training objective focuses on predictive likelihood, not on factual verification. The model is rewarded for predicting likely continuations of text. In many contexts, likely continuations are indeed informative and true because much human text reflects reality. But the training objective does not, by itself, require grounding in an external world. It does not directly ask, is this statement true in reality right now? It asks, what text is likely to come next given the context and the patterns in the data? That mismatch is fundamental. Language plausibility and external truth are related, but they are not identical. A sentence can be highly plausible as language while false as fact. A fabricated citation can look realistic. An invented historical detail can fit the style of encyclopedic writing. A non-existent paper title can sound exactly like a real one. So hallucination is not merely accidental noise. It reflects a structural gap between sequence prediction and world verification. The model has learned patterns of saying, not direct access to reality itself. Let us pause and reflect. This point is worth stating slowly. A language model is optimized to be a good predictor of text, not a built-in fact-checking machine. That does not mean it cannot say true things. Often it does. It means that truth is not enforced in the strongest possible way by the core objective alone. Therefore, when the statistical patterns of text diverge from grounded fact, hallucinations can emerge. Data also matter. The training corpus contains inconsistencies, outdated information, conflicting views, fiction, sarcasm, and errors. The model learns from all of this. It does not automatically know which patterns correspond to reliable truth unless the training and later alignment procedures somehow encourage that distinction. There is also a sequential component. Once an answer begins in a certain direction, the model may continue coherently within that invented frame. In other words, it may maintain internal consistency inside a false narrative. This can make hallucinations feel particularly persuasive. They are often not random word salad. They are structured mistakes. Again, we see the difference between plausibility and truth. Plausibility is internal fit to language patterns and context. Truth involves correspondence to external facts, which may require information beyond the model's static parameters and next token objective. This brings us naturally to retrieval-augmented models and external information. If part of the problem is that the model relies on internal parametric memory, then one response is to supplement that memory with retrieved documents. Instead of asking the model to answer solely from what is compressed into its parameters, one first fetches relevant external text and then includes the text in the conditioning context. Conceptually, this changes the problem. The model is no longer relying only on stored knowledge. It is also conditioning on accessed knowledge. That is a crucial mathematical distinction. Stored knowledge lies implicitly in learned parameters. Accessed knowledge enters explicitly through the prompt or context after retrieval. Retrieval therefore changes the information available at generation time. It enriches the conditioning context with fresh evidence, domain-specific material, or authoritative source. If the retrieval is good and the model uses the retrieved material properly, hallucination can be reduced because the answer is guided by evidence external to the model's memory. It is worth repeating that retrieval does not eliminate probability. It changes it. By inserting relevant documents into context, one reshapes the conditional distribution of the next token. Certain grounded continuations become more likely because the evidence is literally present in the sequence being conditioned on. This is a beautiful example of information flow. The model's output depends on the information available in context. If the context now includes reliable retrieved text, then grounded answers become statistically favored. Of course, this depends on retrieval quality, document relevance, context length, and whether the model cites or uses the evidence accurately. But the principle is clear. Stored knowledge and accessed knowledge are not the same. A model parameter is a compressed statistical trace of training experience. A retrieved document is an explicit external object brought into the current computation. This distinction helps explain why retrieval systems are so important in practice. They compensate for the limitations of static parametric memory, especially when facts are recent, niche, or precise. Let us pause again. A model without retrieval says, in effect, I will answer from what has been absorbed into my parameters and what is present in the prompt. A retrieval-augmented model says, let me first gather additional evidence, then answer conditioned on that evidence. This does not turn the model into a perfect reasoner or verifier, but it changes the statistical problem in a meaningful and often beneficial way. Now we turn to reinforcement learning from human feedback, often discussed as a major ingredient in aligning language models with human preference. The motivation begins with a simple recognition. Next token prediction is powerful, but it is not enough to guarantee behavior that humans prefer. A model can be excellent at continuing text and still be unhelpful, unfocused, rude, verbose, or unsafe. It may imitate patterns found in data without reliably matching what users want in an interactive setting. So one seeks an additional layer of optimization. Instead of training only on what word comes next, one also tries to shape the model toward outputs judged better by humans. This is the broad idea behind preference-based alignment methods. The mathematical intuition is not mysterious. It is still optimization, but the target shifts. Rather than predicting the next token alone, one tries to optimize behavior under signals derived from human judgment. These signals may reward helpfulness, harmlessness, honesty, clarity, or usefulness, depending on how the system is designed. So reinforcement learning from human feedback is not a replacement of pre-training. It is an extension. Pre-training gives the model broad linguistic competence. Preference optimization then tries to steer that competence toward desired behaviors. It is worth repeating that this is still part of the general optimization story. The model is still being adjusted. The loss function is simply more behavior-oriented. The guiding signal now reflects judgment about output quality, not only predictive fit to raw text. How does this work conceptually? Humans compare outputs. They may prefer one answer over another. These comparisons form data. A separate reward model can be trained to predict those preferences. Then the language model is updated so that outputs with higher predicted reward become more likely. This brings us to reward models, preference data, and policy updates. A reward model is an approximation to human preference structure. It tries to learn from examples of human judgments, which outputs are generally preferred. This is already a delicate idea. The reward model does not become morality itself, or truth itself, or usefulness itself. It becomes a statistical approximation to patterns in human evaluation data. Then policy updates change the model's behavior to increase expected reward under that learned signal. In other words, the model is steered toward outputs that the reward model scores more highly. This can make answers more polite, more organized, more compliant with instructions, and often more useful. But it also introduces new complexities. Human preference is not identical to truth. An answer that sounds better may not be more factually correct. A reward signal can improve helpfulness while leaving certain epistemic weaknesses unresolved. It can also create pressures toward verbosity, hedging, or style patterns that humans tend to reward. So again, a distinction is needed. Truth, preference, and usefulness are related, but not identical. A reward model approximates preference, not reality in full. And policy optimization under reward changes model behavior in ways that may be desirable, but also imperfect. Let us pause and reflect. Pre-training teaches the model to speak from patterns in text. Preference optimization teaches the model to speak in ways humans tend to favor. These are different educational pressures. One teaches statistical language continuation. The other teaches socially and practically preferred behavior. The final model reflects both. Now let us turn to mechanistic interpretability and internal structure. Mechanistic interpretability is the effort to understand what the network has actually learned inside itself. Not just what outputs it gives, but what internal computational structures produce those outputs. This is a profound and difficult research direction because neural networks are very large, highly nonlinear, and distributed in how they represent information. Still, one can ask meaningful questions. Are there internal features that correspond to concepts, patterns, or syntactic rules? Are there pathways of activation that implement specific transformations? Are there circuits that support tasks like tracking quotation marks, matching brackets, or resolving references? Can we identify components that carry certain kinds of information from one stage to another? The term circuits is often used to describe interacting subnetworks or pathways that seem to implement specific functions. The term features refers to internal directions or patterns of activation associated with particular kinds of information. The broad goal is to reverse engineer the learned computation. This is very different from merely visualizing outputs. Interpretability in this deeper sense is about discovering structure. It asks whether the network's behavior can be decomposed into understandable internal mechanisms. This matters because if we want to understand reasoning, hallucination, or prompt sensitivity, we may need to understand not only the external behavior of the model, but also the internal organization that supports the behavior. Does the model track entities through hidden states? Does it build temporary internal abstractions? Does it use approximate algorithmic procedures in some cases? These are mechanistic questions. It is worth repeating that neural networks are not transparent just because they are mathematical objects. Everything inside them is numerical, yes, but that does not mean it is easy to understand. Reverse engineering learned distributed computation is extremely challenging, and yet the ambition remains compelling. If one could map internal pathways, discover robust features, and identify computational circuits, one might begin to understand how prompting changes behavior, why certain reasoning traces succeed or fail, and where hallucinations are generated or suppressed. Let us pause and reflect again. Mechanistic interpretability asks whether a trained neural network can be mathematically reverse engineered. Not in a trivial sense of reading off every weight, but in a meaningful sense of identifying functional internal structure. This is one of the most intellectually deep frontiers in the study of language models. And now we arrive at the mathematics of reasoning in large language models. This is perhaps the deepest open question of all. Can reasoning emerge from sequence prediction? Or is apparent reasoning only a surface imitation of patterns in the data? The debate is ongoing, and it is not a simple matter of yes or no. On one side, language models undeniably display behaviors that resemble reasoning. They can often carry out multi-step explanations, follow chains of implication, perform structured transformations, and adapt to compositional tasks. On the other side, they can fail unpredictably, break under distribution shifts, and produce reasoning like text that is not backed by a stable internal logical structure. So what does it mean to reason? That question itself is subtle. Reasoning may involve compositionality, the ability to combine parts into larger structured wholes. It may involve algorithmic behavior, where a sequence of internal operations produces a conclusion through intermediate steps. It may involve inference across multiple stages, not just local pattern completion. A key point is that reasoning should be studied through structure, not only benchmark scores. A model may achieve a high score through shortcuts, memorize patterns, or statistical heuristics that do not generalize robustly. Conversely, a model may show partial reasoning competence even where its benchmark performance is uneven. So we should ask structural questions. Can the model maintain intermediate variables internally? Can it represent abstract relations consistently across contexts? Can it perform multi-step transformations that depend on previous steps? Can prompting elicit more reliable structured inference because it scaffolds the computation? This last point is interesting. Some prompting methods seem to improve reasoning-like behavior by encouraging explicit intermediate steps. One interpretation is that the prompt changes the conditional distribution in a way that makes structured outputs more likely. Another interpretation is that the prompt provides a scaffold within which latent reasoning capabilities can be better expressed. Perhaps both are partly true. It is worth repeating that sequence prediction and reasoning are not obviously identical, but neither are they entirely disconnected. Language data contain many traces of reasoning. Explanations, proofs, arguments, plans, derivations, and decision processes are all present in text. A model trained on such data may internalize statistical patterns that support reasoning-like behaviors. Whether that amounts to genuine reasoning in a strong sense remains under active investigation. Let us pause and reflect very gently. A language model is trained to continue sequences. Yet some sequences describe reasoning. Some sequences contain algorithms in verbal form. Some sequences reflect structured inference. So perhaps it is not so surprising that a sufficiently large model trained on enough data begins to exhibit pieces of reasoning-like behavior. The mystery is not that some structure appears. The mystery is how far that structure goes, how stable it is, and whether it reflects genuine internal computation or only surface regularity. Now let us begin drawing the threads together. We started with decoding and randomness. We saw that training defines a predictive distribution, but generation requires a decoding rule. Greedy decoding gives determinism and caution, but can be narrow. Sampling introduces variation and exploration, but can also increase risk. Temperature, top K, and nucleus sampling do not create new models. They filter and reshape the predictive distribution during generation. So behavior depends not only on what the model knows, but on how we choose from what it knows. Then we moved into in-context learning and prompting. We saw that prompts act as conditioning information. They do not usually retrain the model during interaction, but they reshape the conditional distribution over continuations. Examples, instructions, and framing all matter because they change the sequence context. In this sense, prompting is a kind of conditional control over behavior. It is not magic. It is sequence conditioning. Then we turn to calibration and confidence. A model may sound certain while being poorly calibrated. Fluency and trustworthy uncertainty are not the same. This distinction matters because users can be misled by polished language. The model may produce an answer that feels authoritative even when its connection to truth is weak. From there we examined hallucination. Hallucination is not merely an odd glitch. It reflects a mismatch between language plausibility and external reality. The model optimizes predictive likelihood over text, not direct factual verification. Therefore, plausible falsehoods can arise. The system can produce coherent but invented content because coherence in language is not the same as truth in the world. Retrieval augmentation then offered one response. By bringing external documents into context, we change the conditioning information. Stored parametric knowledge is supplemented by accessed evidence. This can reduce hallucination when retrieval is relevant and well used. Again, the key concept is conditioning. More grounded information enters the sequence, and the conditional distribution shifts accordingly. After that, we considered reinforcement learning from human feedback and related preference-based alignment. Pre-training teaches language continuation. Preference optimization teaches behavior that humans tend to prefer. Reward models learn from human judgments, and policy updates steer the model toward higher predicted reward. This improves usefulness and alignment in many cases, but preference is not identical to truth. So one must distinguish helpfulness, desirability, and factual reliability. We then turned inward toward mechanistic interpretability. Instead of asking only what the model says, we asked how internal structures may support what it says. Features, circuits, and hidden pathways become objects of study. The hope is that one day we may partially reverse engineer the learned computation itself. And finally, we reflected on reasoning. We saw that whether large language models truly reason remains open, but it is not an empty question. Reasoning like behavior can emerge from sequence prediction because language contains structured inference. Still, benchmark performance alone does not settle the matter. We must study internal structure, compositionality, robustness, and multi-step computation if we want to understand what kind of reasoning, if any, these systems possess. Let us pause and reflect one last time. Across all these topics, a small number of ideas keep returning. One is conditioning. Prompting changes conditioning. Retrieval changes conditioning. Examples and context change conditioning. Even decoding choices affect the unfolding condition sequence over time. Another is the distinction between probability and truth. Language models are probability machines over sequences. Truth may correlate with high probability in many contexts, but it is not guaranteed by the objective alone. Another is that behavior is layered. Pre-training creates broad competence. Decoding shapes actual output. Prompting steers local behavior. Preference optimization adjusts style and usefulness. Retrieval supplies external evidence. Interpretability tries to uncover internal mechanism. And another, perhaps the deepest, is that simple local rules can create unexpectedly rich global behavior. Predicting the next token sounds modest. Yet from that modest objective there emerge style, adaptation, planning like traces, confidence, error, and perhaps fragments of reasoning. This is part of what makes the field so mathematically fascinating. As we come to the end, let us gather everything into one slower unifying picture. A large language model is a learned system for assigning conditional probabilities to sequences. It is trained on text, and from text it learns patterns of continuation. But the output we actually observe depends on more than training. It depends on decoding, which selects among possibilities. It depends on prompts, which alter the conditioning context. It depends on whether external information is retrieved. It depends on alignment procedures that steer behavior toward human preferences. When the model reasons well, or seems to reason well, we ask whether structured inference has emerged from sequence modeling. When the model fails, especially in smooth and confident ways, we are reminded that linguistic plausibility is not the same as grounded truth. When prompting works, we see the power of conditioning. When retrieval helps, we see the importance of explicit evidence. When interpretability advances, we move a little closer to understanding not only what these systems say, but how they say it. So the mathematics of large language models is not only about optimization or architecture. It is also about probability, conditioning, information flow, uncertainty, representation, and the relation between patterns in language and structure in thought. It is worth repeating, very softly, that this remains an open field. Many basic questions are still alive. How deep is in context learning? How should calibration be measured in generative settings? What is the best mathematical account of hallucination? How much reasoning can emerge from sequence prediction alone? Which internal structures are stable and interpretable? These questions remain active because the systems are rich, and because our theories are still catching up to their behavior. And perhaps that is a fitting place to rest. We began with generation and randomness, moved through prompting and conditioning, reflected on confidence and hallucination, considered retrieval and human feedback, looked inside the network through interpretability, and ended with the question of reasoning itself. All along, the same gentle lesson kept returning: the model does not operate by magic. It operates through learned statistical structure, conditioned on context, filtered by decoding, and shaped by optimization. The mystery is real, but it is a mathematical mystery, not a mystical one. And that distinction is coming. Because mathematical mysteries can be approached slowly. They can be revisited. They can be described from several angles. They can be studied with patience. So as the subject settles in the mind, perhaps the central image to keep is this: a language model sits at each moment with a distribution over what could come next. The prompt shapes that distribution. Decoding selects from it. External information can enrich it. Alignment can steer it. And from this sequence of conditioned choices, whole conversations unfold. Some of those conversations are helpful. Some are insightful. Some are mistaken. Some only imitate reasoning. Some may contain real fragments of it. And our task, as mathematicians and careful thinkers, is to keep asking what kind of structure makes these behaviors possible. That question remains open. And it is enough for now to rest there.